Here's another linear momentum problem, but in this case we're going to have a moving blade. And a moving blade can happen whenever you are trying to convert the kinetic energy of this fluid into power. So you might see it shown like this. There was a series of blades attached. This object was spinning and you were hitting it with a jet, causing it to rotate, converting the kinetic energy of this stream into torque and power. And we know that power in this case is torque times angular velocity. So now let's work through this, but we're going to work through it more quickly just because we've seen how to attack a jet or a plate that is not moving already. The key distinction in this problem is to be aware of these velocity vectors. The one on the left says that the exiting stream velocity, v1, is aligned with the direction of the velocity of the blade. And so the relative velocity entering the control volume is VR1. On the opposing side, the exiting side, 2, we have a vector that relationship that says that the velocity relative to a fixed reference frame is equal to the velocity relative to this moving reference frame plus the velocity of the reference frame, which is the velocity of the blade. What are we going to do in this problem? We're going to be given the inlet velocity of the fluid, v1, the velocity of the blade, vb, for deflector, alpha, the angle that the fluid is rotated. Again, you have three options when you're thinking about forces and changing the velocity, or I should say, or changing a fluid behavior. Fluid behavior can be changed in terms of direction, magnitude, or profile, how that velocity is distributed. Like this is a classic, or it could be like this. What are we trying to find? We're trying to find reaction forces required to hold this blade at a constant velocity. The velocity 2, vector in vector format, and the power generated. Once again, we work through the Reynolds transport theorem, noting the local and convective terms. We assume steady state, which eliminates that local term. We then decompose the force into f of x, looking at it from a perspective of relative mass flow rate. This is mr, mr. Once again, we're going to assume that the magnitudes of those velocities are not changing on the blade because there is no friction assumed along this blade. There is no spreading into or out of the page. So the velocity magnitude, the total velocity magnitudes along that blade do not change. We go from that decomposed format to a slightly simplified format, m.r, looking at mr2 in the x direction, vr1 in the x direction. What does vr2 mean? It means that the relative velocity exiting in the x direction, vr1 means the relative velocity entering in the x direction. By entering and exiting, I mean relative to the moving control volume. We put in the numbers for mass flow rate: 1,000, 0.02 meters times 0.4 meters. That's the size of the nozzle or jet. This is the relative velocity, where we have V1 is the velocity of the jet exiting a fixed nozzle. So the nozzle is not moving, the blade is. The blade itself is going at 30 meters per second. And we apply VR2x and VR1x. The calculation results in a 268 Newton final value. We repeat that process for Ry, and we calculate 1,000 newtons. To calculate V2 relative to a fixed reference frame, we recognize that it is made up of a relative velocity exiting plus a velocity of the blade. So we have VR2x plus VB for the V2x component. We work through this, and the final value for V2x is 73.3. Finally, V2y is following the same procedure, recognizing that there is no y component of blade velocity, and we end up with 25 meters per second. Pulling those together, we have V2 vector is equal to 73.3 in the I direction plus 25 in the J direction. And those, of course, are in meters per second. Finally, the last calculation for power is basically a force times a distance, force times a rate. In this case, the rate of movement of the blade. So that's 268 newtons times 30 meters per second. Since the blade does not move in the y direction, we don't have a VBY component. That results in a final power calculation of over 8,000 watts. This would be the power applied to the moving blade by the jet as it exits the nozzle. So in review, we have a moving blade. We have been given the velocities of the jet, the blade, the angle that the blade is rotating the jet. We also know something about the nozzle size. Finally, we look for Rx, Ry, V2, and power generated. We go directly to the Reynolds transport theorem. We simplify. We decompose. We look at the velocities carefully. And we finally do a power calculation. I hope this was useful. And if you have questions,